Thank you for tuning in to the North Carolina Center for After School Programs STEM Resources. Today we're going to do an activity called Water for Life. What we're going to do is build a model of two different types of aquifers. Now, aquifers are the underlying rock in which groundwater is contained. So if you get your water from a well, then your water source is an aquifer. Frankly, most of the water on Earth is salt water and we can't drink it. But the most abundant source of fresh water on the Earth is actually the polar ice caps, which we don't live near. So the second most abundant source of fresh water is groundwater. And throughout the world, people use groundwater for drinking water and for irrigation and livestock and industry and everything else that we might possibly need. Now, groundwater is a potentially renewable resource if it's part of the water cycle and it gets filled back up faster than we can use it. Now, let's talk about the water cycle. We're going to be simulating several different parts of it. We're going to be simulating precipitation. We're going to be simulating runoff, in which the water flows across the ground, and then infiltration, in which the water itself moves down between the little soil particles until it collects in these rocks called aquifers. Today we're going to compare and contrast two different kinds of aquifers, and we're going to compare their properties and see which ones we might prefer, especially if we're in an area in which they might be vulnerable to pollution. So the first one that we're going to do is gravel and then sand. The easiest way to get these is to go to a Home Depot or Lowe's and get the giant bags and then break it out into little sandwich bags, handfuls of about a handful and a half of gravel and about a handful and a half of sand. The other thing you need clear plastic cups, water. I love these. These are graduated cylinders and they're very inexpensive, available from Carolina Biological for less than about $2. And another real science tool that we're going to use today is a dropping pipette. Now, dropping pipettes are important because they help us modulate the amount of water that comes out, and it kind of simulates the raindrops in precipitation. The other thing, you need little tiny coffee stirrers cut in about half. And these are going to be your wells, and some food coloring to simulate pollution. So let's get started. First thing we're going to do is we're going to look at the spaces in between. How much water can an aquifer hold? Now, those spaces, little holes, are called pores, and the measurement of that is porosity. Let's look at the difference between the gravel and the sand. First, which one do you think will hold more water or have a higher porosity? Will it be the gravel or the sand? Now, in order to measure this accurately, we're going to use a graduated cylinder. And why I think this is a great tool for kids to get started with. First of all, if you have a big cup like this, it's real hard to get a precise measurement. And we want our kids to be using metric measurements. Oops, spilled some. And that's the other component. So we're going to pour, I did a pretty good job, 25 milliliters. Now, I want you to look really closely. Can you see that the top of the surface is curved? That's called a meniscus. And what happens is that the surface tension of the water is holding on to the narrow tube so that you get a more accurate and precise measurement. So this graduated cylinder is right at 25 milliliters. Now, if you get too many, you can take a couple drops out, put it back in. But we're going to measure exactly how much porosity the gravel has and then compare it to the sand. Which do you think is going to hold more? Now, this is the part where we simulate precipitation. And you can have the kids sprinkle very slowly across the top of the aquifer, and it can take a super long time, which also simulates infiltration. But for speediness sake, I'm going to pour it very slowly across the top. You didn't see it. Now, how much do you put in? Well, here's the secret. You want to pour it slowly and let it soak in. Not too fast. Can you see it filling up at the side? The air holes, the pores, the zone of aeration, are being filled with water, becoming the zone of saturation. And right here, where you can see the water level, that's called the water table. And the water table rises and falls seasonally and according to how much precipitation you get. In a drought, the water table will be lower. So that was 25. We're going to need some more. Oops. Oh, that's too much. Take out a little bit with your dropping pipette so that you're right down to the meniscus. And then you want to pour this part slowly. Can you see the water table rising? This is one of the reasons why our lake levels change after we have a big rainstorm. Okay, so I'm near the surface and I can start seeing little puddles forming. That means that this is completely saturated. So I'm done. And you look, 25 plus 26, 27. This held 25 plus, take 2 off, 23, so you've got 48, roughly 48 milliliters in here. Now let's try the sand. The sand is tricky. Do you think it will hold more or less water than the gravel? And remember, that's our porosity, is the measurement. Okay, I'm at 25. Now, I really think with sand especially, you want to drip it across the top. Because you'll see as you drop the water, the spaces really contract and move. And if you pour too much too fast, it will flood your sand aquifer, and then you have to start over, and kids usually get pretty irritated with that. So when we're talking about the water cycle, now you're looking at precipitation, runoff, infiltration, and you can see how the pores are filling up, and actually the sand itself is changing shape and sinking a little bit. This is really neat when you talk about karst topography, where you have underlying limestone, but that's a different lesson, where you get underground caves and sinkholes and such. So I'm looking at this, and quite honestly, it's pretty close to saturated. Can you see that it's dripping down? Now, if you pour it faster, this is what happens. Pour it slowly. Can you see it changing shape? Pour slowly. And that's the zone of aeration becoming filled with water, so that's zone of saturation. We're going to add some more, so that's 25 plus you see it shrinking down? Okay, so I'm going to say that that is 25 plus 10, 11, 12, so that's 37. So which held more? In this case, the gravel held more, had a higher porosity than the sand. Now let's check out permeability. Permeability is the connectedness of the holes. So in order to demonstrate this, we're going to look at the food coloring. Oh, but before we put the non-point source pollution, we want to put a well in, and that's the little tube here. Go ahead and put that down inside. Now, this is our non-point source pollution, meaning it's carried by runoff across the land. Now, water is the universal solvent, so the same thing that transports plants, the minerals that plants need, is also the same thing that can carry pollution into the groundwater. Now, let's see which of these wells is more easily contaminated by the pollution. So now is when you're going to pull these out. Can you see that immediately? So the gravel has a higher porosity, meaning it can hold more. Now sometimes, depending on your sand, you might find that the sand has a higher porosity. It just depends on the grain size, and this was a little damp. So this, though, the permeability, it happened immediately, and with gravel, that definitely happens faster. So immediately, 1 milliliter, you saw the red. I'm going to rinse it out so it's not contaminated. And not only is it harder to get water in general out of our sand aquifer. Can you see how slowly it fills back up? That also means that its connectedness for the permeability of the pollution, it means it's a little less vulnerable to the pollution itself. Now, there's sand coming up out of the well, but there's no red dye yet. It's really tricky when you're using these dropping pipettes. I find that they're much cheaper to purchase at Carolina Biological. I got 100 for about $6, but then you have to be careful that it closely matches the diameter of whatever straw you're using so it forms a seal. So in this case, I used the narrow ones and then a coffee stirrer. You can use the larger dropping pipettes and then use a regular drinking straw. So I'm still not finding, oh, there's the first little bit. Just a teeny tiny little bit of red right in there. So what that means is that your gravel has higher porosity, which means it can hold more, right? And higher permeability, which makes it easier to get the water out, easier to refill, but also more vulnerable for pollution. When you've got your sand, you still have a high holding capacity or high porosity, but the pore spaces aren't as connected so that the water doesn't flow as quickly through it, which means it also makes it less vulnerable to pollution. So when you're talking about these little wells, if you look right along the edge in here, you can see that right along the edge of the straw, the pollution tends to migrate down straight into the aquifer, and that's what happens in real life. So we talk about this concept called wellhead protection, because if your well becomes cracked, then whatever pollution can make its way straight into the aquifer. So when you're looking at groundwater resources in North Carolina, some of the things in the news that you may hear about pesticides or fertilizers getting into wells, nitrates specifically, which can cause health problems and make pregnant women and young children and infants sick. You can also hear about different point sources that have contaminated groundwater. In our lesson for our older children, we talk a little bit about Chemours and Gen X in the Wilmington area, and also the coal ash that has leaked and contaminated some groundwater from Duke Energy's coal ash sites. So those are two extensions that are local. You can talk about protecting groundwater and why it's so important and how much of it is actually a source for our drinking water throughout the world. So thank you very much.